Okay, so this podcast has to do with nuclear decay. And nucleuses, which is what the nuclear is talking about here, nucleuses can undergo decay and fall apart in really 3 different ways in general chemistry. If you want to take another chemistry, there's more like 5 ways. We're going to talk about 3 right now. So nuclear decay comes down to really this graph that I have down here. I'm going to expand it and then we'll kind of get rid of it. But here's a graph that has number of neutrons on the y-axis and number of protons on the x-axis. And you can kind of see, let's see if I can write on top of it, is we have 10 protons right here, we have 10 neutrons, and this line, this dark line, is simply a 1-to-1 ratio of protons to neutrons. So you can kind of see that, and then the other part is, each of these little red dots represents various isotopes that we know of. So for example, if we go to this 20, right here, element 20 has all these isotopes, has a bunch of them because it has a bunch of red lines kind of going vertically. So the most common of these isotopes is always a 1-to-1 ratio for elements 1 through 20. Alright? So again, elements 1 through 20, we're talking about atomic numbers here, have approximately equal number of protons and neutrons. Protons and neutrons. Right, and a P plus is going to be our shorthand for proton, and an N with a 0 is our shorthand for neutrons. And then notice, element's really 21, and we're going to call it through 82, we have a bunch more neutrons for every proton. Alright? So we're going to say neutrons are greater, and as we add more and more protons, they become even more and more greater than our protons. Alright? Part of that, you can kind of think of it in terms of, we have protons which are in our nucleus. Nucleus is incredibly small, and we have this positive charge smashed into the same space. So does that want to stay like that? Is that stable? No, positive charges want to repel each other. So think of the neutrons as kind of the glue that kind of helps hold the nucleus together. So as we add more and more protons, we're going to have to add more and more glue to overcome all those repulsions that the positive charges are causing on each other. Alright, so we kind of have more instability between 21 and 82 because we don't have equal numbers of protons and neutrons. And then anything over 83 is considered radioactive, and all that means is the naturally occurring isotopes of these elements tend to fall apart and give off radioactive particles, okay, as they decay. So really the rest of our notes deal with that. So I'm just going to simply get rid of this table. Alright, and we're going to go back to basically 3 types of decay. The first one is going to be called alpha decay. And an alpha particle is really the same thing as a helium nucleus. Alright, so helium nucleus we might just say is He. It has a mass or an atomic number of 2 and a mass number of 4. And because it's just the nucleus, it has no electrons. So it has 2 protons but no electrons. So it really has a positive 1 or positive 2 charge. Okay? Because there's 2 protons with no electrons to cancel out that positive charge. So it could be written like this. Another way we sometimes write it would be using the Greek symbol alpha, which is like this, and again it's going to be a 4 and a 2. And typically we don't necessarily worry about the +2 charge. If you think back to Rutherford's gold foil experiment, he had, I think, uranium, which is the lead, and it was emitting alpha particles. So he knew the nucleus had to be positive because the alpha particles, which are positive, were being repelled, back towards him and hitting the gold foil in the opposite direction. So that is alpha. And the other thing we're going to say about it, alpha particles can be blocked. So they're not super dangerous unless they get inside our bodies, but they can be blocked by skin and paper, or by skin or paper. So for the most part, these can't hurt you. again, unless you ingest them somehow. And back during the Cold War, whenever the U.S. was kind of at war with Russia, the communist regime, one of the ways that communists would kill people was actually to get alpha particles in a drink, kind of spike their drink with that. They would then drink that, and inside our bodies, because just inside we have kind of cell membranes and stuff, those can't block alpha particles. These are really big because they're made up of 2 protons and 2 neutrons, so that they're fairly large particles when it comes to the atomic level, and they just wreak havoc and would cause fairly severe radioactive poisoning pretty quickly. So that's alpha. The next type of decay we can have is beta decay. And a beta particle is simply an electron. Alright? So just betas are electrons. But instead of those electrons coming from the outside, it's actually coming from the inside. And the electron arises from a neutron turning into a proton. Alright? So if I were to put that graphic back up, if there's too many neutrons to proton, if that ratio is off, sometimes that neutron can actually decay, and it turns into proton particles, turns into quarks and muons and stuff like that. And when they reassemble themselves, instead of reassembling themselves into a neutron, they reassemble themselves into a proton. And in that proton being formed, an electron is given off. So again, this electron comes from the nucleus. So an electron from nucleus you might put in your notes. And the way we abbreviate it is E for electron, with a -1 charge. Alright? And then it has 0 mass. And because it has a negative charge, the atomic number actually goes in as a -1. Okay? And again, we're not too concerned about charge. The other way we might write it is using the Greek symbol, which is this. Okay? Kind of like a B with a tail. And again, it's a 0 -1. These typically need they can penetrate most things that are about 2 centimeters thick. Alright, so 2 centimeters to 3 centimeters. Can go through metals, 2 to 3 centimeter metals, is what we might say. Lead does a pretty good job of blocking beta rays just because lead is so dense. But otherwise, it goes through skin, goes through pretty much everything. Alright? And then the last particle is gamma rays, or gamma particles. And these is just high energy rays, really. Alright? High energy particles, we'll just call it that. High energy particles. And the way we abbreviate these, they are fairly uncommon, and we're not going to see them in equations. But a gamma symbol is simply that. All right, kind of like an alpha diving or a fish diving, but that's a gamma particle, and it is just 0, 0. All right, and that is pretty much nuclear decay.